Lesson 5.1, Fundamental Identities. So in this lesson, we're going to learn all of the different trig identities, or at least the common ones, and then we're going to use those identities to rewrite complicated trig expressions into simpler ones. You don't have to write these identities down, they're going to be on your sheet, but the ones we're going to work with the most, the reciprocal identities, the quotient identities, and the Pythagorean identities, as well as sometimes we will incorporate the cofunction identities and the even-odd identities. These ones on this page we probably won't refer to as often. The first identity we're going to discuss is the Pythagorean identity, which is sine squared theta plus cosine squared theta equal to 1. And we can go through a short explanation on where that identity comes from or why it's true. If we think about the unit circle and construct a right triangle, it's called the unit circle because the radius is 1, so the hypotenuse of this right triangle would be 1. We have our length y and the length x. If we use some basic trig functions, we know that the sine of theta is equal to the opposite over the hypotenuse. So the sine of theta would be equal to y over 1, which would just be y. Similar idea for the cosine of theta. Cosine of theta is equal to the adjacent over the hypotenuse, which in this case would be equal to x over 1, which is just x. Since this is a right triangle, we can also use the Pythagorean theorem to set up an equation because a squared plus b squared is equal to c squared. So in this case, we would have x squared plus y squared equal to 1 squared. Now using substitution, I know sine of theta is equal to y, so I can substitute that in, as well as the cosine of theta is equal to x. So instead of x, I'm going to write cosine of theta, that quantity squared, plus instead of y, we have the sine of theta, that quantity squared, equal to 1 squared is just 1. And then the simplified version of this, the squared is applied to the function cosine. So we would write it as cosine squared theta. Same for the sine squared theta. So that is why the sine squared theta plus cosine squared theta will always be equal to 1. Next, we're going to briefly talk about where those other two Pythagorean identities come from by starting with the main Pythagorean identity. So if I take sine squared theta plus cosine squared theta equal to 1 and divide that whole equation by sine squared theta, well, sine squared theta divided by sine squared theta is 1. Cosine squared theta divided by sine squared theta, if we use the quotient identities, cosine over sine, is equal to cotangent squared theta. And then 1 divided by sine, we would use a reciprocal identity. We know 1 over sine, that relates to the cosecant function, so 1 over sine squared theta would be cosecant squared theta. We can use a similar idea over here, except this time divide by cosine squared theta. So now if I take sine squared divided by cosine squared, that is equal to tangent squared theta. Cosine divided by cosine is going to be equal to 1, equal to 1 over cosine squared theta is going to be equal to secant squared theta. So we just start with our main one, divide by either sine squared or cosine squared, use reciprocal identities or quotient identities to rewrite it in these other two forms. Example 1, we want to use trig identities in order to simplify this expression, sine cubed x plus sine x cosine squared x. In this one, we're going to use ideas of algebra. Because we have two terms, we want to determine if they have anything in common, which they both have a factor of sine x in common, so we're going to factor that out in front. So if we factor sine x out in front, we'd be left with sine x times sine squared x plus cosine squared x, which this is our Pythagorean identity, what's in the parentheses. So we have sine x times 1, which is just going to simplify down to sine x. So we took that fairly complex expression, used trig identities to rewrite it as just sine x. Example 2, again, we want to simplify this expression. We have secant x plus 1 times a quantity secant x minus 1, all divided by sine squared x. In the numerator, you can recognize that this is a difference of squares pattern, so we should multiply this out in the numerator using the FOIL method. So I would take secant x times secant x, which would get me secant squared x, secant x times -1, which is minus secant x, secant x times a positive 1, which would be a positive secant x, and then 1 times -1 minus 1, all over sine squared x. In the numerator, you notice if we use that method that our negative secant x and positive secant x will cancel out. You don't have to show that step if you know right away that those are going to cancel each other out. So now we're left with secant squared x minus 1 over sine squared x. If you look at the numerator, we can rewrite secant squared x minus 1 as tangent squared x because that is one of the Pythagorean identities. So now we have tangent squared x over sine squared x. One skill or strategy you should try to use is to rewrite these trig functions in terms of sine and cosine. Because if you can rewrite all of them in terms of sine and cosine, sometimes you can get things to cancel out. So we need to use our quotient identity to rewrite tangent squared x. And tangent x is equal to sine over cosine, so we can rewrite that as sine squared x over cosine squared x. So now we have sine squared x over cosine squared x divided by sine squared x over 1. We have a fraction divided by a fraction, so we could take our numerator and multiply by the reciprocal of the denominator. The sine squared x in the numerator and denominator cancel each other out, leaving us with 1 over cosine squared x. The last thing we need to use is a reciprocal identity. We know cosine is related to secant, so 1 over cosine squared x is equal to secant squared x. And now that's our simplified answer. So we started with a fairly complicated expression, secant x plus 1 times secant x minus 1, all over sine squared x. Use various trig identities in order to rewrite that in a fairly simplified trig expression, secant squared x. Example 3, we want to simplify the expression cosine x divided by 1 minus sine x minus sine x over cosine x. So in this one we have two rational expressions. If we're going to combine this into one, we have to have a common denominator. So we have to multiply the first fraction by cosine x over cosine x, and the second one we have to multiply by 1 minus sine x over 1 minus sine x, because then we will have a common denominator. Once we multiply those expressions through, we're going to leave the denominator in factored form, but we're going to simplify the numerator. So we're taking cosine x times cosine x, and then over here we're subtracting the quantity of sine x times 1 and sine x times negative sine x. So now we get cosine squared x minus the quantity sine x minus sine squared x in the numerator. We can distribute this negative through, which gets us cosine squared x minus sine x plus sine squared x all over cosine x times the quantity 1 minus sine x. If you look in the numerator, we have a cosine squared x plus a sine squared x, which is our main Pythagorean identity, so that expression will simplify it down to a value of 1. Now we have a common factor in the numerator and denominator of 1 minus sine x, which is going to simplify out, leaving us with 1 over cosine x. Last step, we need to use a reciprocal identity. Cosine is related to secant, so this simplifies down to secant x. So that fairly complicated expression that involved two different rational expressions, we use trig identities to simplify that all the way down to secant x. Last example, we want to find all solutions for the equation 2 sine squared x plus sine x equal to 1 on the interval from 0 to 2 pi. In this particular problem, if we try to simplify, it's going to get very complicated. So there's a little trick we can use. So we're going to set sine x equal to y. And what that allows me to do is rewrite this expression over here. So now if I substitute y in for sine of x, I can rewrite this as 2y squared plus y equal to 1. Now this just looks like a quadratic equation. If we're going to solve a quadratic, we need to set it equal to 0. So this would be 2y squared plus y minus 1 equal to 0. And now we need to factor this. And it factors into the quantity 2y minus 1 times the quantity y plus 1 equal to 0. Using the zero product property, we would set each of these factors equal to 0. So I have 2y minus 1 equal to 0 and y plus 1 equal to 0. Now, since I simplified this, I can go back and substitute back in the sine of x in for y. So my new equation over here is 2 sine x minus 1 equal to 0. The one over here is sine x plus 1 is equal to 0. So I want to simplify to get sine of x by itself. In this case, I would get sine of x is equal to 1/2. And over here, I would get sine of x is equal to -1. Now we're looking for the interval from 0 to 2 pi. So think about your unit circle. Where on the unit circle do you have a y value of 1/2? Well, that occurs at pi over 6, as well as 5 pi over 6. And then we also want to determine where on the unit circle do we have a y value in our ordered pair of -1. That occurs at one place, which is 3 pi over 2. So these are the x values, the values in between 0 and 2 pi, that if we plugged back into our original expression, 2 sine squared x plus sine x equal to 1, would make this a true statement.